We're now going to be looking at the concept of linear combinations. So the definition of a linear combination, if V is a real vector space and I've got some vectors that are from V, I've got some scalars, then a linear combination of those vectors is the following vector. So what we do is a multiple of one vector plus a multiple of another vector, and so on. That forms a linear combination. So for example, 3 times vector 1 plus 2 times vector 2 plus 0 times vector 3, any real numbers, all the way plus minus 10, let me not say plus minus 10 times vector 6, any combination is called a linear combination like this. So firstly, notice that this forms a vector again in that set. How do I know that a linear combination is in the set itself? Because that set is closed. It's a vector space, so it's closed under scalar multiplication, and it's closed under vector addition. So a linear combination of those vectors is any combination like that, and there could be 0. Some of these numbers could be 0, so we don't necessarily have to use all the vectors, but a linear combination is another vector that's back inside that set. So let's take a look at a real example. Let's look at the elements I, j, and k in R3. Just to remind you, I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. So if I look at a linear combination of elements of S, so for example, 4i plus 3j minus 2k, that'll give me 4, 0, 0 plus 0, 3, 0 plus 0, 0 minus 2. And that gives me the vector 4, 3, minus 2. All right. 4, 3, minus 2 is again in the set R3. We know R3 is closed under vector addition and scalar multiplication. Now, we don't know anything about S because S wasn't given us as a vector space. S is just a set with 3 elements in. And for this matter, S is not a vector space. But I've got a set with 3 vectors in, a subset of R3. I know R3 is a vector space. So any linear combination of elements of this set is again in R3. And that's what linear combinations look like. So we can take any linear combination. I can say minus a half I plus pi k. These are both real numbers. That would be the vector minus a half, 0, and pi. That again is an element of R3. All right, so linear combinations, that's what we mean. Some scalar multiple of the first one plus a scalar multiple of the second one plus a scalar multiple of the third one. All right, but just to remind you, the set S only has those 3 elements in. We know nothing about the fact that it's a vector space, and it isn't a vector space, but we know R3 is a vector space. So let's look at this set S. It's got 2 ordered pairs. I know this is a subset of R2. So these are just 2 elements. This set S is not a vector space because it only consists of 2 elements and neither of them is a 0. So it's not a vector space, but I've got 2 elements from R2. So any linear combination of those will again be an R2. So for example, 4 times 4, 1, minus 2 times minus 1, 2, which will give me 16 plus 2 is 18. 4 minus 4 is 0. That is again in R2. So linear combination. So that's what we mean by linear combinations. A scalar multiple of one vector plus a scalar multiple of the other vector. Now we need the concept of linear combinations for our next concept, which is span. So yet again, here I've got 2 vectors, 1, 2, 3, 0, 1, 2. That's a subset of R3. So any linear combination of those two, 4 times 1, 2, 3, plus 0 times 0, 1, 2. That's what a linear combination is. That gives me the vector 4, 8, and 12. And that's again in R3. So a linear combination of those vectors. So that's what we need to look at. What is a linear combination? And what can we do with them? And that brings us to our next section, which is on the span of a set.